Synoptic 1, Test 3 Review 2021. Section 1, Frontogenesis and Frontogenical Circulations. The definition of frontogenesis is the intensification of the horizontal temperature gradient. Frontogenesis happens as a result of three things. 1. Horizontal deformation of the flow, shear and confluence terms. Vertical deformation, the tilting terms. And 3. The unequal or differential diabatic heating. It can be calculated with the following equation. F, or frontogenesis, equals d dt times the absolute value of del subscript 3 theta. This equation represents the rate of increase or decrease of the magnitude of the 3D temperature gradient with time following a parcel. This is a Lagrangian equation. For the simplified frontogenesis equation, I won't be reading it out here, but I will go over the terms, A, B, C, and D. Term A is the shear term, and here, shearing advection changes the orientation of isotherms and is important around fronts, troughs, and outflow boundaries. B is the confluence term and acts to pack isotherms together and stretch them out. Think of stretching out silly putty. C is the tilting term. When adiabatic cooling in one direction and warming in the other occurs, this increases the horizontal thermal gradient. This causes one side of the temperature gradient to sink. Tilting is important in the upper levels, where it can cause the tropopause to sink several kilometers and form a frontal layer. It's also important near mountains due to change in slope of the terrainium and or wind speed along the terrain. D is the diabatic heating / cooling term, and it can be from latent heating, sensible heating, or radiational cooling / warming. Since it's a non-advection process, this term involves no winds. An example: in the winter, a large difference between the temperature of snowy surfaces and adjacent water bodies. So, for example, a snowy surface has a cool temperature and a lake or ocean has a warm one, and heating and cooling from below sets up local fronts here. Another example is that cloud cover prevents parts of Earth's surface from heating during the day. A front is generated between heated clear air and cooler air under the cloud cover. Near cold fronts, the shear and confluence terms tend to work together, but near warm fronts, they tend to oppose each other. The Pedersen frontogenesis equation. The two terms in resultant deformation are stretching and shearing deformation. The angle beta represents the angle between the isotropes and the axis of dilation. Since beta is being multiplied by 2 with a cosine, you would want values of beta that, when multiplied by 2, maximize the cosine value if you want to maximize frontogenesis. So, when beta is greater than 45, you have frontolysis. The wind separates the isotherms. This is because cosine when the degree is greater than 90 is negative. When beta is less than 45, frontogenesis, where wind compacts the isotherms. Here, cosine is less than 90, which is positive. Deficiencies of kinematic frontogenesis is very important. One deficiency is that frontogenesis takes days and not hours, and this isn't always true. A cyclone could develop very rapidly. Another deficiency is that we don't take into consideration of response of the thermal wind from our change in our thermal gradient. So basically, it does not account for all factors of the atmosphere. Section 2, Climatology of Cyclones. Regions for cyclogenesis in the U.S. are most frequently along the east coast and in lee of the Rocky Mountains. Here the lee side refers to the side sheltered from the wind, the west side in this case. The Rocky Mountains are a natural barrier to cyclones coming from the Pacific. In January, anticyclones tend to form in northern Canada and in the Great Plains region of the U.S. In July, anticyclones tend to form in the southwestern Canada region. With season, the frequency of highs and lows shift. But for all seasons, the ratio of cyclones to anticyclones is about 1.8. Both cyclones and anticyclones are more frequent in January than July. The Norwegian cyclone model. In the early stage of the cyclone model, the low is not vertically stacked. It is not under the lowest heights. Wind is parallel to the height contours aloft, and cyclonic curvature is happening. Moving the warm and cold front, the trough will become more negatively tilted with time. The trough will become deeper because of warm air advection and cold air advection powering it. The circulation will become greater, thus more cyclonic. Later stage, the occlusion stage. Here the trough is more negatively tilted aloft, and they are now vertically stacked. On the study guide, there are graphics for this process, and you might want to look them over. Section 3, Conveyor Belts and Cyclogenesis. The definition of a conveyor belt is that conveyor belts came from us realizing that there are sharply defined boundaries that differentiate airstreams of vastly different moisture contents. There are warm conveyor belts, cold conveyor belts, and dry conveyor belts. A conveyor belt consists of an ensemble of air parcels having nearly the same theta W or theta E value, starting from a common initial location which travels over synoptic scale time periods, also known as over 18 hours. So for the types of conveyor belts, we have warm conveyor belts, and warm conveyor belts are a ribbon of low-level air which originates in the warm sector and transports warm air from lower to upper levels. This generally goes in a poleward direction. For the cold conveyor belt, it's a ribbon of low-level air which originates north of the warm front, traveling eastward toward the surface low. It wraps cyclonically around it. And for the dry conveyor belt, it's a ribbon of upper-level air which originates in the cold, dry air of the upper troposphere. It wraps cyclonically around the base of the upper-level trough, sinking as it approaches the surface low. So, the concept of system relative flow. The reason that a weaker system can still acquire relatively strong warm and cold conveyor belt flows is because a weaker low moves faster than a stronger one. And according to system relative flow, this means that the conveyor belts will still be strong. A stronger low, however, moves slower, but the circulation is stronger, meaning you still get strong warm conveyor and cold conveyors. Definition of a trowel. The trowel stands for trough of warm air aloft. It defines the apex of the warm sector at successively higher levels. Essentially, it is the cyclonic part of the warm conveyor belt that wraps around the northwestern sector of the cyclone. And there is a graphic for this as well that you might want to look over. Another section, satellite imagery and cyclogenesis. During the baroclinic leaf phase, there's an S shape in the clouds. The new surface low forms or is forming at the accipit position, which could be called the joint or pivot point that connects the cold and stationary front. This point is generally tied to the inflection point, which is where the highest point on that bump of the clouds is. And once again, this is accompanied by a graphic. Next, you have the formation of the cusp feature. The cusp feature is that point in the clouds that is rotated back around and now looks like the bottom of a comma. When this feature forms, it indicates that the cutoff low is at least 500 millibars deep. We know that the max intensity of the surface low has been reached when the occlusion process begins. The cyclone's center begins to cut off from the warm sector. The low will continue to deepen as long as there is warming anywhere in the column or divergence is greater than convergence in the column. Section 4, Basics of Cyclogenesis. So, In the equation for divergence associated with a shortwave trough, the dA represents the average divergence from wave trough to crest. A represents the amplitude the shortwave trough of the shortwave trough. V is the wind speed at the level of the shortwave trough. VL is the wind speed at the level of non-divergence, or LND. F is the Coriolis parameter, and L is the wavelength. So in the equation, you can clearly see that the average divergence from wave trough to crest is maximized for shortwave troughs with a large amplitude and with high wind velocity relative to the wind at the LND. However, the wavelength has by far the largest influence on the average divergence because it has a third power attached to it. Smaller wavelengths indicate far more divergence. Relationship between convergence, divergence, and vorticity. So, from the viewpoint of following a parcel, when following a parcel above the LND, upper level convergence will cause an increase in vorticity, and upper level divergence will cause a decrease. Remember the ice skater analogy here. Negative vorticity advection is convergence, and positive vorticity advection is divergence. When thinking about it at a point rather than following a parcel, the ice skater analogy also works here. Divergence aloft means low-level convergence. The surrounding air pushes on the column, which makes it stretch upward and thus spin faster, like an ice skater. Convergence at a point means more vorticity, and divergence at a point means less. Remembering the basic mass continuity principles and associating them with the ice skater analogy will help here as well. We look at vorticity advection at 500 millibars because 500 millibars is very close to the level of non-divergence. And at the level of non-divergence, vorticity only changes due to advection. Relationship between ageostropic winds, divergence, and vorticity. A sharp trough has strong curvature and shear, therefore it has a strong vorticity maximum. Downstream from the vortmax, you have divergence aloft, which means rising air below. A sharp trough will also have strong ageostropic motions. We will see divergence of the ageostropic winds at 500 millibars. The stronger curvature of the 500 millibar flow, the greater this divergence of the ageostropic winds will be. The stronger the divergence of the ageostropic winds, the greater the divergence of the winds at 250 millibars will be. Baroclinic wave theory states that for a surface cyclone to develop, proper conditions must be present at the surface, at mid-levels, and aloft. When a short wave disturbs the flow at mid-levels, it creates an instability in the flow known as baroclinic instability. There is a baroclinic feedback loop that allows the low to continue deepening as long as certain things are met. So in phase 1, as the short wave approaches the long wave, the positive feedback process begins. As the trough deepens, curvature of the trough increases, which promotes divergence downstream of the trough. At the low level, there is cold air advection on the back side of the low and warm air advection on the front side of the low. Surface pressure has a circulation around it. These advections of temperature deepen the 500 trough even further and build the ridge. Since the trough and ridge have even more curvature, the divergence increases, and more divergence equals lower surface pressure, equals more low-level temperature advection. So, in summary, the temperature advection causes a deepening of the trough and the steepening of the ridge, which increases the curvature, and more curvature means more divergence. And more divergence means lower surface pressure, which means more low-level temperature advection as circulation increases. Final section, Pedersen's development equation. You'll have to label and explain the terms here, and the equation is on the review sheet. But I will read the terms out here. Term A. Term A is the local time tendency of the surface geostropic relative vorticity. Essentially, it's a parameter to measure surface cyclogenesis. Term B. Term B states that positive advection of geostropic absolute vorticity will lead to surface development. Term C states that surface development is favored when there is an integrated maximum of warm air advection, especially if the warm air advection / cold air advection field is highly contorted or warped. Term D is the adiabatic term, also known as the break term. In a statistically stable atmosphere, a local maximum of ascent leads to decreasing surface vorticity. Descent in a stable atmosphere leads to surface cyclogenesis, as in Lee-side cyclogenesis. In a neutral atmosphere, this term is 0. In a saturated environment, one should use the moist adiabatic lapse rate instead of the dry one. This term is less effective at breaking cyclogenesis if the environmental lapse rate is closer to moist adiabatic. Finally, term E states that a localized maximum of diabatic heating leads to increased surface vorticity and therefore surface development. Latent heat and sensible heating effects can increase the effectiveness of this term. Tropopause undulations. An undulation in the troposphere is like a dip in it. A tropopause undulation can happen when the air below the tropopause becomes cooler and thus causes it to dip down. The 3 stages of tropopause undulation with respect to a developing surface low. In step 1, the pressure gradient on the tropopause increases, with the low portion sinking much more than the high portion ascends. The cyclone at the surface shifts increasingly from underneath the upward sloping tropopause undulation to a position under the lowest tropopause level. Vertical location of relatively warm air above the surface changes from the lower troposphere to lower stratosphere as the cyclone develops. The troposphere above the surface low cools and the tropopause lowers, while the stratosphere warms.